Dear students, today I am going to start a new topic, that is circular motion. We studied the topic one-dimension motion. In the one-dimension motion, a particle moves along a straight line. So when we speak about the circular motion, the particle moves in a plane. In a circular motion, a particle moves along the circular path. So this is the circle, the center of the circle. If the particle moves along the circular path, the motion of the particle is called circular motion. Let us observe some examples of the circular motion. The motion of the satellite around the earth is an example of circular motion. And one more example, let us consider a wheel rotating about one axis like this. A wheel is rotating about this axis. This is the wheel. If I take any particle or any point on the wheel, the motion of the point on the wheel is an example of circular motion. Why? As the wheel is rotating about one axis, this particle move in a circular path. So the motion of this point is an example of circular motion. The next observation, let us consider the watch. So if I take any hand in the watch, the tip of the hand, whether seconds hand or minutes hand or hours hand, it moves in a circular path about the center of this dial. In every case, what is happening? A particle is moving in a circular path. So the motion of the particle is circular motion. Now, so I define some important terminology in the circular motion. Important terminology in circular motion. The first one is angular position, so to decide the angular position of the particle in a circular motion, we need origin and the reference line. For example, this is the circular path of a particle. So this is the center of the circle. I call this point as a origin, and let us draw one horizontal line. I call this horizontal line as a reference line. So to decide the angular position of any particle, we need these two. One is origin, other one is the reference line. Suppose this is the position of the particle P. We should draw the position vector of this P with respect to the origin, and we have to measure the angle between this reference line and this position vector. Now this angle is called angular position of P. Angular position. So what I am doing? Just I am drawing a position vector of P with respect to the origin and reference line. The angle between the position vector and reference line is called the angular position. Now let us define angular position. It is the angle made by position vector of a particle with respect to origin with a reference line. So one more important thing, the angular position of this particle depends upon the choice of origin, also on the reference line. Clear? It depends upon the choice of origin, also on the reference line. Right. Now let us discuss angular displacement. Angular displacement. This is the circular path of a particle. Now let us call this is the reference line. This is called origin. Right. At a particular instant of time, the P is the position of the particle. Let us draw the position vector of P like this. Now this is called angular position of the particle P. This angular position is measured from the reference line. After a small interval of time, the particle P is moving to P dash. The particle is going from P to P dash. So then what happens? The position vector of the particle moves from this position to this position, means now the position vector of that particle rotates through some angle. It is rotating through this angle. Now this is called angular displacement of the particle. Now I can define what is angular displacement. It is nothing but the angle through which this position vector rotates in a given time interval. Suppose if I take a time interval delta t, in this time interval through what angle this position vector is rotating is called angular displacement. So let us write the angular position of P dash. This is the angular position of P dash, say it is theta 2. Now this angular position is theta 1, this angular position is theta 2. Now this angle is known as angular displacement. Angular displacement delta theta equals to theta 2 minus theta 1. So what does theta 2 minus theta 1 indicate? The angle through which position vector of the particle is rotating in a given time interval. So now I define the angular displacement. The angle through which the position vector of a particle rotates in a given time interval. This is called the angular displacement. Now the angular displacement of the particle only depends upon the choice of the origin. It does not depend upon the reference line. It only depends upon what? So it depends upon the origin but does not depend upon the what? Reference line. Now what are the dimensions of angular displacement? Angular displacement is a dimensionless quantity. It is dimensionless quantity means the dimension formula is m0, l0, t0. The SI unit of angular displacement is radian. This is radian. The symbol is RAD. There are some other units for the angular displacement. Those are degrees and revolutions. So there is a relation between the different units. 2 pi radian equals to 360 degree is equals to 1 revolution. This is the relation among the different units. So now I can find the relation between the radian to degree and degree to radian. So what is that? 360 degree equals to 2 pi radian. From this, 1 degree is equal to 2 pi by 360 radian. We can use this relation to change the units from degree to radian, right? Yes. Now, if angular position is measured in the anti-clockwise sense, that angular position is taken with the positive sign. It's very important. So, this is the reference line, this is the origin. Now, this is the position of the particle. Now, this is the position vector of the particle. We know the angular positions are always measured from the reference line. So, if I measure the angular position of this particle in the anti-clockwise direction, this angular position is taken as positive, and if angular position is measured in a anti-clockwise sense, means it is the position of the particle. Now, position vector of the particle, if I measure like this in a clockwise sense, here we measured in the anti-clockwise sense. If I measure the angular position in the clockwise sense, this angular position is taken with negative sign. Now, when a particle moves in a circular path, the finite angular displacements are considered as scalars. The finite angular displacements means what? 10 degree, 20 degree, 30 degree. These are the finite angular displacements. These are considered as a scalars. So we know if angle is measured in the anti-clockwise direction from the reference line, that is positive. If angle is measured in the clockwise direction from the reference line, that is taken as negative. To get the total angular displacement, we have to add these positive and negative angular displacements. So we will get the total angular displacement when the positive and negative angular displacements are added. The algebraic sum of the positive and negative angular displacements gives the net angular displacement of a particle. Now let us go through one example. This is the position of the particle. Now this angle is 30 degree. This angle is 30 degree. Generally, we have to convert this into radians, because generally we measure in the radians. So how do you describe? How do you describe the angular position of particle? Number one, here we can measure the angular position of this particle in the anti-clockwise sense as well as in the clockwise sense. Let us see what is the difference if it is measured in the anti-clockwise sense or in the clockwise sense. First, anti-clockwise sense. If we measure in anti-clockwise sense. So this angular displacement theta is equal to just it is plus 30 degree, because we will measure the angle like this in the anti-clockwise sense. The angles measured in the anti-clockwise sense are positive. Let us convert this into radians. We know 1 degree is equals to 2 pi by 360 radian, because we know 360 degree is equal to 2 pi radian, 1 degree is equal to 2 pi by 360. Now let us convert into radians. That is 30 into 2 pi by 360. So what will be this? This is 30, this is 1, 2, this is pi by 6. Okay, so this is plus pi by 6, because it is measured in the anti-clockwise sense. What happens if the same angular position is measured in the clockwise sense? If I measure like this, that symbol is minus, because we are measuring in the clockwise sense. Now the angular displacement theta is equals to minus, so this total angle is equals to 2 pi minus, let us subtract this value. What is that? Pi by 6. This 2 pi minus pi by 6, that is minus, this is 12 pi minus pi, that is 11 pi by 6 radian. So why I indicate with minus? The minus indicates here we have measured the angle in the clockwise sense. It is clear. If the angle is measured in the anti-clockwise sense, it is positive. If the angle is measured in the clockwise sense, it is the negative. Yes. Elementary angular displacement are considered as a vectors. What is the meaning of elementary angular displacements? Suppose if you see a particle is moving in circular path like this, so like this, in a small time interval, through what angle can that particle rotate? Through a smaller angle it can rotate. If I take the length of this arc, if I take the arc length, it is almost straight line. So I can consider the elementary angular displacements are the vectors, but finite angular displacements are the scalars. To know the direction of the elementary angular displacements, means smaller angular displacements, we have to use the right hand thumb rule. Let us see that. Suppose one particle is moving in a circular path in the anti-clockwise sense. It is the sense of motion of the particle. So I want to know what is the direction of the angular displacement, elementary angular displacement. We have to use the right hand rule. Simply, first we have to stretch our right hand in such a way the thumb and remaining fingers are perpendicular to each other. Now if we curl the right hand fingers in the direction of the motion of the particle, the stretched thumb indicate the direction of the angular displacement, right? Here the particle is moving in a anti-clockwise sense, so I am curling my fingers in the anti-clockwise sense. Then this thumb indicates the direction of the angular displacement. What is the direction of this thumb? This thumb is perpendicular to the plane of rotation and coming out from the plane of rotation. That means this thumb is parallel to the axis of rotation. Suppose take this is the axis about which a particle is moving in a circular path like this. Clear? Now I am curling my fingers in the direction of rotation. This is the axis about which the particle is in a circular motion. This gives the direction of angular displacement. The direction of angular displacement is parallel to the axis of revolution. So I can call this angular displacement is an axial vector. Why it is axial vector? This vector is along the axis of revolution, parallel to the axis of revolution. So angular displacement is a axial vector. Let's see what is the direction of angular displacement when the particle in a circular motion moves in a clockwise sense. Suppose now the particle is moving in a clockwise sense like this. So on the plane of the board the particle is moving like this. So this is the axis along which the particle is revolving. To know the direction of angular displacement, we have to use the right hand thumb rule. Just observe how I am doing here. So the particle is moving in a clockwise sense like this. So I am curling my fingers, right hand fingers, in the direction of the motion of the particle. This thumb indicates the direction of the angular displacement. How is the direction of this thumb? The thumb is pointing perpendicular to the plane of rotation. Also it is pointing into the board. Finally the direction of angular displacement is along the axis of revolution. So this is called axial vector. Clear? It is clear. What is clear? The direction of angular displacement is perpendicular to the plane of rotation. Perpendicular to the plane of rotation. Now let us discuss next angular variable, that is angular velocity. Angular velocity. So we know in the one dimensional motion we know the linear velocity. What is the meaning of linear velocity? The rate of change of linear displacement is called linear velocity. The same way, the rate of change of angular displacement is called angular velocity. Let's see. Suppose theta 1 is the angular position of the particle at a time t1, theta 2 is the some other angular position of the particle at t2 seconds. Now, so you can say that angular velocity of the particle is written as average angular velocity is equals to theta 2 minus theta 1 by t2 minus t1. So this is nothing but delta theta by delta t. Now the average angular velocity is defined as angular displacement divided by time taken, total angular displacement divided by total time taken. Yes, this you can say this average angular velocity also a vector quantity. You can write this delta t vector by dt, right? Now what is the meaning of instantaneous angular velocity? Instantaneous angular velocity. The instantaneous angular velocity is represented as omega instantaneous is equals to limit delta t tends to 0, that is delta theta by del t, which is equals to d theta by dt. So this is the instantaneous angular velocity. Now I can define the instantaneous angular velocity. It is the limit of average angular velocity as delta t approaches to 0. Very simple. A limit of angular velocity when delta t approaches to 0 is called instantaneous angular velocity. Very simple. If delta t is very close to 0, that average angular velocity is called as instantaneous angular velocity. Yes, it is also a vector quantity. So to know the direction of the angular velocity, here we use the right hand thumb rule. What is the right hand thumb rule? For example, suppose a particle is moving in an anti-clockwise sense like this. So this is the axis of rotation. For example, it is the axis of rotation, right? So now I am taking the rotation like this, now like this. So it is the axis of revolution. The particle is moving in an anti-clockwise sense like this. To know the direction of angular velocity, we should use the right hand thumb rule. You see how I am finding the direction of angular velocity. I am curling the right hand fingers in the direction of the rotation of the, in the direction of the motion of the particle. Then the stretched thumb is in the upward direction, means it is parallel to the axis of revolution. So what can I say here? The angular velocity also axial vector, because it is parallel to the axis of revolution, right? Axis of revolution. Yes, this is the, now it moves, if the particle moves like this, now this is the direction of the angular velocity like this. Now if the particle moves like this, the clockwise sense, like this, I am taking like this, the particle is moving in a clockwise sense like this. So I need to curl my right hand fingers in the direction of revolution. Then this indicate the direction of the angular velocity. Now it is the direction of the angular velocity. Like this we can find out the direction of the angular velocity. Both average angular velocity, instantaneous angular velocity, both are the vectors. Both are the vectors. Now dimensions of angular velocity are t power minus 1. The SI unit of angular velocity is radian per second. Radian per second. You can also call revolution per second. Yes, radian per second or revolution per second. Let us see one thing. A particle is moving in a circular path like this. Yes. So what is the expression for angular velocity? Omega is equals to total angular displacement by total time taken. So if the particle completes one revolution, then the angle made in this process is 2 pi. If the particle completes 2 revolutions, that is 2 pi into 2. If it completes 3 revolutions, this is 2 pi into 3, like this. If the particle completes n revolutions in t seconds, then the angular velocity in radian per second is represented by, so 2 pi n by t. This is the angular velocity. When the particle completes n revolutions in t seconds, then angular velocity omega is equals to 2 pi n by t, right. Frequency and time period. So we define the term frequency in circular motion when the particle is moving with a constant linear and angular speed. That is very important. When the particle moves with a constant linear and angular speed, we define the term frequency. What is the meaning of frequency? The number of revolutions completed by the particle in 1 second is called frequency. The number of revolutions completed by a particle in 1 second is called frequency. Suppose a particle is moving in a circular path like this. Yes, moving in a circular path like this. So the particle is completing. So let us say one thing. What is time period? The time taken to complete one revolution is called time period. Yes, a particle is completing one revolution in t seconds of time. It is completing one revolution in t seconds of time. Then how many revolutions are made by the particle in 1 second? That gives the frequency. Yes, in 1 second the time taken to complete one revolution is t seconds. Then in 1 second how many revolutions are completed? Simply x is equal to 1 by t. This x is nothing but frequency. So frequency, so you can represent with f or nf is equal to 1 by t. So number of revolutions completed in 1 second, that is called frequency. Yes. So let us define angular frequency. Angular frequency. We know that the angular velocity of a particle in the circular motion is given by omega is equals to d theta by dt. So let us write this, let us rearrange this as d theta is equal to omega into dt. So I told you the frequency is used whenever the particle moves with a constant linear and angular velocity. So here omega is constant. So listen, if a particle complete one revolution, what is the angle completed by that particle? From 0 to 2 pi radians, let us integrate it from 0 to 2 pi radians, d theta equals to omega is constant, this is equals to dt. The time taken to complete one revolution is called time period. So the time is taken from 0 to t. We know that integral d theta is equals to theta and integral dt is equals to t. Write this, theta limits should be taken from 0 to 2 pi and here limit should be taken from 0 to t. So in the place of theta, first we should write the upper limit, that is 2 pi minus 0, that is equals to t minus 0, that is, so we left omega here, this is omega, 2 pi is equals to omega into t. Now omega is equals to 2 pi by t. Now this term 2 pi by t is called angular frequency. Now I can write we know 1 by t is equal to f, omega is equals to 2 pi f. Now this is the frequency. Now we can call omega as angular frequency. Yes. Now this is the angular frequency. Let us do one example. So a particle is moving in a circular path like this. Now this is the center. This is, I am taking it as origin, a reference line. So it is the position of the particle P. Now let us write the position vector of the particle with respect to O. This is the position vector. It is making an angle alpha. The angular position is alpha. Now let us take one more reference point, say A. So draw the position vector of P with respect to the A. This angle is equals to beta. I told you one thing. The angular velocity of this particle depends upon the choice of origin, means reference point. Here the angular velocity of this particle P is different with respect to O and A. How it is different? I can say that angular velocity of P with respect to O equals to d alpha by dt. Yes. Now angular velocity of P with respect to A is represented as d beta by dt. So these are different. So the angular velocity of a particle with respect to different origins, different points will be different. Let us discuss a few problems based on angular speed, angular velocity. Yes. The first problem is an insect moves in a circular path. Travels n1 revolutions in anti-clockwise direction and n2 revolutions in clockwise. Direction. So an insect moves in a circular path, travels n1 revolutions for time t1 seconds in anti-clockwise direction and n2 revolutions in a clockwise direction for a time t2. Then find angular speed of a particle during the time t1 plus t2. Yes, what is the given problem? An insect moves in a circular path, travels n1 revolutions for time t1 in anti-clockwise direction and n2 revolutions in a clockwise direction for a time t2. Then find the angular speed of a particle during the time t1 plus t2. Means we have to find out angular speed of the particle over the time t1 plus t2. Yes. So what is the formula for angular velocity? So angular velocity, here we need to find angular speed. The magnitude of the angular velocity is called angular speed. So angular velocity is equals to total displacement by total time taken. Here, for example, the particle is moving in a circular path like this. Yes, an insect moves n1 revolutions in an anti-clockwise direction for a time t1. So I can say that I can say one thing, theta 1 is equals to, so 2 pi n1 plus 2 pi n1. Why plus 2 pi n1? Yes, that insect is moving in a anti-clockwise sense, completing n1 revolutions. If the insect complete one revolution, the angle completed by that is 2 pi. If it is complete n1 revolutions, the angle equals to 2 pi n1. And why should I take plus sign? That insect is moving in a anti-clockwise direction. So theta 1 is equal to plus 2 pi n1. Clear? So one more thing. Theta 2. What is theta 2? And that is moving, that is completing n2 revolutions in a clockwise direction for a time t2. So I can write that 2 pi n2 minus 2 pi n2. Why? This is as the angle is being measured in the clockwise sense, it is minus, and if it completes one revolution 2 pi, as it is completing n2 revolutions, minus 2 pi n2. Now net angular displacement is equals to theta 1 plus theta 2, that is equals to 2 pi n1 minus 2 pi n2. 2 pi n1 minus 2 pi n2. Now angular speed omega is equals to theta by net angular displacement theta by total time. That omega is equals to, what is the net angular displacement here? 2 pi n1 minus 2 pi n2. Let us take in mod by, what is the total time taken for this process? It is moving in the anti-clockwise sense for t1 seconds and in a clockwise sense for t2 seconds. So the total time taken is equals to t1 plus t2. So after the simplification, now the angular speed omega is equals to 2 pi n1 minus n2 by t1 plus t2. Units are radian per second. Clear? Like this we have to solve a problem. Yes, is it clear? Let's go for another problem. Yes, this is the clockwise direction, this is the circular motion of the, it is a circle, center of the circle. Now let us indicate the two positions of the particle. This is the position 1, it is the position 2. So this is the reference line. This angle is say 30 degree, this angle is say 60 degree. A particle is moving from position 1 to 2. So in a time half second, 1/2 second. So now we have to find out what is the angular speed of the particle when it is moving in a anti-clockwise sense and clockwise sense. As shown in the figure, a particle is moving along the circular path from point 1 to 2 during 1/2 second. Then find number 1 angular speed when the particle moves in anti-clockwise direction. Find angular speed when particle moves in clockwise sense, a clockwise direction. So this is the problem we have to do. If you are very much clear on the topic angular speed, what is angular speed? Magnitude of the angular velocity is called angular speed. Let us try to do this problem. A particle is going from point 1 to 2. So what is the angular speed of that particle? It is going from 1 to 2 in 1/2 second. Let us find the solution for 1. Means angular speed when the particle moves in a anti-clockwise direction. You see, if the particle moves from point 1 to point 2, through what angle it is moving? So what is the angular displacement of this particle? Generally, yes, now the angular speed omega is equals to, you can write theta 2 minus theta 1 by t2 minus t1, means total time taken. Yes. So say this is the final position. So this angle is theta 2 and it is the initial position. This angle is theta 1, right? Here I will write this theta 1. You will measure the theta 1 like this, because angular displacements are always measured from the reference line. So this is the reference line. We should measure like this. So this angle is negative, means minus 30 degree. Why? This angle is measured in the clockwise direction. So if the angle is measured in the clockwise direction, that angle is negative, minus 30 degree. The next, what is the theta 2 value? So this is the final position. You should measure the theta 2 like this angular displacement, this angular position. How you are measuring? In the clockwise anti-clockwise direction. So this angle is taken with positive sign. So theta 2 is equals to plus 60 degree, theta 1 is equal to minus 30 degree. So how will it change? Then omega is equals to, what is the value of theta 2? Plus 60 degree minus of theta 1, minus 30 degree by theta 2 minus theta 1. This is, the particle is going from 1 to 2 in 1/2 second, that is 1/2 second. So what is this? This is equal to 60 plus 30, 60 degree plus 30 degree by 1/2. This is equal to 90 degree by 1/2. So you can write this is pi/2 radian. 90 degree is equal to pi/2 radian. So pi/2 by 1/2, this is equal to pi radian per second. Pi radian per second. Yes, this is the angular speed of the particle when that moves from 1 to 2 in the anti-clockwise direction. Next, let's go to the solution of second part. So what is this angle? What is the meaning of clockwise sense? Now the particle is going from 1 to 2 in the clockwise sense. Clockwise sense means it has to move like this. So we have to measure this angle. What is this angle? This total angle is equal to 2 pi radian. Total circle angle is equal to 2 pi radian. But I want this angle only. So let us write now angular displacement theta is equals to 2 pi. From 2 pi let us subtract this angle, that is pi/2. What is this? 4 pi minus pi, 3 pi/2. But you should take this in the negative sense. Why we should take in the negative sense? We are measuring the angle in the clockwise direction. So now average angular speed omega is equals to theta by t. So that is theta. What is the value of theta? Minus 3 pi by 2 by 1 by 2. That is equal to 3 pi radian. Generally, this minus indicates the sense of rotation, the sense of revolution. Minus means the particle is moving in a clockwise direction. If I take its magnitude, then omega is equal to 3 pi radian per second. What minus indicates? The minus indicates the sense of revolution. This is the problem, right? Let's go for another problem. Yes. So this is the at t is equal to at some time instant it is the position of the particle, at some other time this is the position of the let's take this is the position of the particle. Okay. Now the particle is moving from P1 to P2. Yes, the angular position of the first particle is 30 degree, and now this is equal to 90 degree. Right. Now we have to find out angular speed of that particle. Find the angular speed of a particle when it moves from P1 to P2 in 2 seconds. Very clear. In anti-clockwise direction. Very simple, that is moving like this. So very simple, we know what is that the magnitude of the angular velocity, angular speed is equal to what is this? Theta 2 minus theta 1 by T2 minus T1. What is this? Is the net angular displacement by total time taken. Yes. So first theta 1 is equals to plus 30 degree. Why plus 30 degree? This is theta 1. We are measuring in the anti-clockwise direction. Anti-clockwise direction means positive. What is the theta 2 value? Theta 2 is equal to, so we should measure every angular position from the reference line. This is the theta 2 value. The theta 2 is equal to plus 90 degree because we are measuring in the anti-clockwise sense. So theta 2 minus theta 1 is equals to 90 degree minus 30 degree, which will be is equal to 60 degree. 60 degree. So we have to convert this into radians. So theta 2 minus theta 1 is equal to 60 degree means pi by 3 radian. Pi by 3 radian. We know how to convert the radians. So we know 1 degree is equals to 2 pi by 360. Here what is this? 60 degree. 60 degree. We have to convert 60 degree into radians. So 60 degree is equals to that 60 into 2 pi by 360. So 0 cancel. So this is equal to pi by 3 radians. Clear? Right. This plus pi by 3 radians. Next, the time taken T2 minus T1. T2 minus T1 is equal to what is the time taken by the particle to go from P1 to P2? It is taking only 2 seconds of time. Now the average angular speed omega is equal to pi by 3 by 2. So you can write pi by 6 radian per second. This is the angular speed of the particle when it moves from P1 to P2. Yes, is it clear? Right. Next problem. the angular position or angular position of a particle is given by, so theta is equal to a minus bt plus ct square. Then find average, then find angular speed. Yes, we have to find the angular speed. So what is given? The angular position of the particle is given by theta is equal to a minus bt plus ct square. Then find angular speed. So here we have to find instantaneous angular speed. So because the position of the particle changes, the position of the particle is depending upon your time. So by using this relation you can find out the instantaneous angular speed. So that is theta is equals to a minus bt plus ct square. Now instantaneous angular speed is equals to d theta by dt. So that is d by dt of, what is the angular position? A minus bt plus ct square. You know the differentiation process, already you learned it. Now you can say that, so dA by dt means differentiation of constant, where a, b, c are the constant. Differentiation of this constant means d by dt of a minus b is a constant, that is d by dt of t, plus c is a constant, that is d by dt of t square. So we know, so d by dt of any constant equal to 0. This is 0. So this is minus b into dt by dt. This means 1 plus, d by dt of t power n is equals to n into t power n minus 1. You know this. So c into, what is the n value? 2. 2 into t power n minus 1. 2 minus 1, that is 1. So you can say that omega is equal to minus b plus 2 ct. This is the angular speed of the particle. You can find the angular speed of the particle at any instant of time. So where b and c are the constants, you can find what is the angular speed of the particle at 1 second, 2 seconds, 3 seconds. You can find out angular speed at every second. Yes, this is the way how to find out the angular speed, instantaneous angular speed. Now let us discuss angular acceleration. Angular acceleration. So suppose omega 1 is the instantaneous angular velocity of the particle at time t1 seconds. Omega 2 is the instantaneous angular velocity of the particle at a time t2. Then the instantaneous means the average angular acceleration alpha is written as alpha average is equals to omega 2 minus omega 1 by t2 minus t1. What is this? This is the change in the angular velocity by time taken. The rate of change of angular velocity is called angular acceleration. Okay, the rate of change of angular velocity is called angular acceleration, which is represented by alpha average. Right. So what is the instantaneous angular acceleration? instantaneous angular acceleration. So it is very simple. Instantaneous angular acceleration is equal to limit delta t tends to 0, that is, you can write this as delta omega by delta t, that is delta omega bar by delta t, which is equals to d theta by dt. Yes, so it is converting from delta omega to d theta. D theta means d omega, sorry, d theta not d omega. This is what a smaller angular velocities. We are changing from finite angular velocities to smaller angular velocities. So this is the instantaneous angular velocity. I am defining this. It is the limit of average angular velocity as delta t approaches to zero. So here this angular acceleration is a vector quantity. The direction of angular acceleration is in the direction of change in the angular velocity. In the direction of change in the angular velocity. Now let us write one conversion, different forms of angular acceleration. Alpha is equals to, you can write, so d omega by dt, but you know omega is equals to what is that, d theta by dt. Can you write? So angular velocity is equals to angular displacement by time, this is d theta by dt. So you can write d square theta by dt square. So finally alpha is equals to, what is this, d omega by dt, that is equals to d square theta by dt square, and is equals to omega into d omega bar by d theta. So these are the, this is also a very important relation, angular acceleration, right? So when alpha equal to 0 means when angular acceleration is 0, that particle is said to be moving with a constant angular velocity, right? Let us see one thing. Suppose alpha is equals to d omega by dt. So let us see one thing. A particle is moving in a circular path like this. It is the axis of revolution, right? When mod omega increases, then what will happen? D omega by dt will become positive. When omega increases, this d omega by dt will become positive. Positive means alpha and omega both are in the same direction. Very simple. When omega increases, when angular velocity increases, then angular acceleration is parallel to angular velocity. That means suppose it is moving like this in the anti-clockwise sense like this. So this is the direction of the angular velocity, direction of angular velocity like this. Yes, and this is also direction of alpha. Why? When mod omega increases, angular velocity increases, alpha and omega are parallel to each other. We know in the linear velocity, in the one dimension motion, when velocity increases, linear velocity increases, acceleration is in the direction of increasing velocity, means the direction of velocity and acceleration are same. When velocity decreases, the direction of acceleration is opposite to the direction of velocity. The same rule I apply here. Suppose in the same sense, here a particle is moving in a anti-clockwise direction in a circular path, right? So if omega decreases, then what will happen? D omega by dt will become negative. D omega by dt will become negative means alpha will be negative, which means direction of alpha is opposite, anti-parallel to direction of omega. That means when omega decreases, this is the direction of omega, then direction of omega and alpha are anti-parallel to each other. Is it clear? Very simple. When omega increases, direction of angular acceleration is parallel to omega. When omega decreases, then direction of angular acceleration is anti-parallel to omega. So like this you can find out the directions of angular acceleration. In the next class we will discuss the relation between the linear and angular variables.